So while the people are still joining, let me welcome everyone to this last episode of qmeets, but only for this year. We will return in January with some quantum thermodynamics. But today we are extremely happy and grateful to have two such distinguished speakers. Let me properly introduce the two. So on the experimental side, we have Antoine Browaeys. I hope I say this correctly, please.
Yeah, perfect. Yeah.
Oh, thank you. Nice. His research focuses on synthetic quantum antibody systems and, of course, the hot topics of today, that is quantum simulation and computing. In particular, he's interested in controlling a few atoms in optical lattices via strong dipole-dipole interactions. So something that occurs very naturally for Rydberg systems, for which he is undoubtedly an internationally recognized expert of. If you don't know much about dipole systems, you may want to, and Rydberg systems, you may want to look into one of his reviews that appeared in Nature Physics. He also has an extraordinary CV, I would say. He did his PhD under Alain Aspect, so under the Nobel Prize winner of 22, and the first postdoc under William Phillips, another Nobel Prize winner. He returned to CNIS, the Institute of Optics at Paris-Saclay, 2003, and has recently been interested in commercial applications as well. He is the co-founder and chief, how is this called? Scientific officer, right? Of Pascal, which is one of the biggest neutral atom-based quantum computing firms in the whole world. On the other side, in the theory side, we have Tommaso Roscilde. His research also wanders around quantum antibody systems, but also quantum information. In his PhD, he started with quantum magnetism, and he's still very interested in understanding phases of matter, in particular those that you can realize in tabletop experiments, so basically with AMO devices. He also has a lot of work that is related to spin squeezing and understanding entanglement generation, and I also wanted to highlight that he's an expert in numerical methods. Now, they both started to collaborate over the recent years a lot. In particular, they reported the first realization of strong scalable spin squeezing 2 years ago, which was published in Nature, and started to study the low energy physics of 1 and 2D Rydberg systems in Antoine's group. They will today talk about results in this direction, and in particular in results that are on how to characterize the non-equilibrium quench dynamics in these systems via a technique that Tommaso invented, which is called quench spectroscopy. We are very thankful to have you here, and now the stage is yours.
Thank you very much, Tobias. Thank you very much, Daniele, and thank you a lot for putting together this and organizing these meetings. This is very nice to have such initiatives. And indeed, what I'm going to discuss are the experimental side first, and then you'll have the input from Tommaso on the theory aspects, knowing that everything I'm going to discuss was actually initiated by the discussion and by the ideas that Tommaso and his team had over the years. So the title of the talk is The Importance of Being Dipolar. So you will see where dipole comes into play, but that allows you to perform quantum simulations in regimes that are actually pretty hard to calculate. So hopefully I will show you where this comes into play. And the platform we're going to use is indeed the platform that we have developed at the Institute of Optics, which is based on the Rydberg atoms. So before I actually start, let me just introduce the team at the Institute of Optics. So in our group, we've got other projects that are not Rydberg related, but let's say 1/3 of the group is working on the Rydberg platform that already gives you a scale of the number of people that you need to run such operations. So it's not completely negligible. So we have 3 permanent staff members, Thierry, who is more in charge of the Rydberg setup, and Igor, who is more in charge of light scattering in our group, and myself. And we have very talented PhD students and postdocs. And the thing which, once again, is very important to us here is the collaboration that we always have with theorists. I mean, we have a platform, and I wouldn't say it, if I could say it bluntly, and they have the ideas. And so essentially, they suggest things, and hopefully they learn from our naive questions about their system. So for what I'm going to discuss, this was mainly inputs from and ideas from Tommaso and Fabio in Lyon, together with Filippo and Saverio, for what I'm going to discuss. But we also benefited from a collaboration with the group of Norm Yao in Harvard, and in particular Marcus Binz, who was very instrumental in many of the work I'm going to discuss. So just to put it very bluntly and very generally, what we're doing is we're trying to assemble atoms and quantum system atom by atom in order to study many-body physics. And broadly speaking, this means trying to understand how an ensemble of very strongly interacting quantum particles interact. And you need those three words: interaction, quantum, but also strong interactions, so that it's actually difficult to track numerically or by any other mean the behavior of the system. So what we're truly doing in the lab is actually not necessarily trying to understand extremely deeply real-life material, but building toy many-body systems to develop an intuition about those many-body systems, going from the simple, which is to say essentially controlling one or a few atoms, to more complex systems, understanding the role of noise, how it plagues or do not plague actually the system. The second thing is, by doing so, we also trigger new theoretical methods. I mean, the number of atoms that we know how to manipulate those days are larger than the best numerics when the atoms are very strongly interacting. So that poses a challenge and hopefully a teaser for the theorists to develop new theoretical or numerical methods. And the last thing, you've already mentioned that, and I'm not going to discuss that too much, but this is a very interesting work we've done with Tommaso. Those machines, what they do really is they also produce quantum states of matter. In the particular case we're going to discuss, those are spin systems or analog to spin systems. For example, you can generate states that are called squeeze states that are useful for metrology. So I think that really what we're doing can be summarized by those 3 points. And once again, it's by doing this route that maybe one day we can understand better real-life systems. Superconductivity is one example which is always quoted and which requires understanding and developing intuition on these many-body systems. Quantum magnetism is another example. And the very far and long-term goal is, of course, trying to use everything we've gained on the understanding of those systems to develop really applications. I mean, those strongly correlated systems, which is what I'm describing here, have actually in applications in material science and photoelectric devices, in chemistry and all this. So we're not there yet. I mean, the company you mentioned has in mind trying to explore that. This is very long term, but I mean, we need to kind of go this route from toy model to understand real life systems to hopefully use the knowledge to develop applications. So in our case, what we do is we combine two things to build our synthetic system. We combine arrays of individual atoms. I will say more in a minute, but essentially each dot corresponds to one and only one atom, separated by its neighbor by a few micrometers, so very far, so that the atoms do not interact. They are just trapped in space. And we combine that with interactions that allows them to interact very strongly by promoting them to what is called Rydberg interactions. So a bit more about the platform. So this is something that actually started now a long time ago, 25 years ago, at the Institut d'Optique, by the demonstration by Philippe Grangier that by taking a laser beam and focusing it very tightly over a size of typically 1 micrometer, this can act as a trap. So essentially, you can be in a regime where an atom is going to be attracted at the location where the intensity is the largest. So that's essentially the focal plane of an aspherical lenses that we use to focus the light, and which in our case is placed in vacuum. So there are many ways of doing that, but this is what we do. So after many years, so we managed to develop these platforms, make sure that by laser cooling the atoms or by sending light on these atoms, the atoms could fluoresce, and we could collect these fluorescent lights onto a camera. So essentially here you got two beams, and the one that ensures the trapping, which is not resonant with any atomic transition, so it doesn't generate fluorescence. And the second one, which is resonant, which we use for cooling, for imaging. And with this one, we can collect the light and see the atom really in the usual sense where you collect the light scattered by an object. So now, if you want to have many of these atoms in order to do many body physics, what you do is you place on the path that ensures the trapping, you place diffraction grating, essentially. It's slightly more complicated than this. Essentially, it's a device that imprints a phase, but at the end of the day, all the phases diffracts the light. You have diffraction spots, and each of the diffraction spots can act as a trap. And so at the end of the day, the kind of structure we can build atom by atom are 1D, 2D, even 3D structure. Each of the dots here corresponding to an image that you collect on the CCD camera of the fluorescence light emitted by the atom. So this is really seeing the atoms arranged in a snake-like configuration, in a circle, in 2D square array, triangular arrays, or any kind of geometry in 2D, and even arranging them. So there's this Eiffel Tower, which is of course useless for physics, but kind of cute to look at. And today, with this platform, we can reach about 1,000 atoms. So that's about the number of atoms that can be manipulated using this platform. So, as I said, the atoms, they are very far from each other, from their neighbors, and therefore they do not interact. So we promote and enhance the interaction by promoting them to Rydberg states. So Rydberg states are states that are highly excited states. So we do the excitation with laser beams, so starting from very well prepared atoms using all the techniques that people have developed over 20 or 30 years. We use a 2-photon laser excitation to excite them to a state 60s1/2. So 60 is the principal quantum number, and the rest are just the usual spectroscopic notation. But what is important is that for everything we're going to say, we're going to live in these Rydberg manifolds where the atoms can stay for quite a long time, so typically a few hundred microseconds. And so this will be the mapping onto spin down and spin up. So the two states that we will consider are states nearby Rydberg states that act as a two-level system. From the point of view of the interaction, what is interesting is that those two states, those two atoms, can exchange their state. So for example, if you place an atom in a P state, the other one in an S state, you may have the decay of one atom from up to down, so P to S, emitting virtually a photon, which can be captured by the second atom. So that's the dipole-dipole interaction. And that results into a spin exchange interaction. So essentially, you can have a configuration where they can coherently exchange their state as a function of time. And this is illustrated here on an experiment we've done where you place just two atoms separated by 15 micrometers. You prepare one up, the other one down, and after some time you measure the state of each of the atom, and what you see is that they do exchange their state in a phase opposition, which is exactly what you want. So this implements an Hamiltonian, which is the C3 over R3, because it's a dipolar interaction. Sigma plus, sigma minus, that are the Pauli matrices, which the theorists actually usually prefer to write XX plus YY, and so that's the reason why it's called the XY spin model. And that implements a spin model for spin 1/2. Okay, and the thing which is interesting is that the interaction range is 1 over R cubed, and you will see that this is where dipolar comes into play. So now what I'm going to discuss are two examples of experiments we've done together with Tommaso. One where we try to measure the low energy excitations of the system in terms of spin waves. So that will be the quench spectroscopy of the dipolar magnet. And the second one, I will just kind of flash how you can prepare the ground state in one dimension and how it connects to another concept in many body physics, which is called Luttinger liquid. So let me first start by the first experiment that came out actually this year. And that we started actually a long time ago together with Tommaso. So once again, the question we're asking here is reasonably simple. So you just take an ensemble of spin 1/2. They are pinned in space, so nothing moves. The atoms do not move, and they are pinned. They carry a spin 1/2. They implement this XY model with an interaction, which is 1 over R cubed. So that's the dipolar interaction. So I showed you that it applies to Rydberg platforms, but it actually applies to many other platforms. It applies to polar molecules. It applies to magnetic atoms. It can also apply to defects in solid that usually can interact via their magnetic moment. So it's again a magnetic a mu square over R cubed type of interaction. So it's not the physics we're going to look at is not restricted to the Rydberg platforms. It's something which is generic to spin system interacting with long range interactions. The thing that makes dipolar exciting is the fact that it immediately leads to the presence of what is called frustration. So frustration is something that makes challenging the simulations of the systems. And it can be illustrated in this way. assume that you got a square array and that you have an antiferromagnetic interaction. So the antiferromagnetic interaction is going to favor the antiferromagnetic order. So I mean, along the edges of the square, you will have an antiferromagnetic ordering. And that results into the fact that along the diagonal, you have a ferromagnetic ordering. But the point is that this ferromagnetic ordering now is in competition with the natural antiferromagnetic interaction, which would have a tendency to destabilize and to lead to an antiferromagnetic order. Of course, it's weaker because it's on the diagonal and the distance is larger, but because it's 1 over r cubed, it only decays slowly as a function of time. And as a consequence, this destabilization can have a strong effect on the many-body properties of the system. So this is what we're going to look at, and in 2 cases. So the first one will be the out of equilibrium dynamics with long-range interactions. So if you want to understand the law of the excitation of a spin system, usually the picture that people have in mind from their elementary condensed matter physics class is the concept of spin waves. So essentially, this is illustrated by this graph where you just take a chain of spins and you try to look at it classically. So you just try to excite the system and you've got this kind of spin wave, which is to say you try to impose some oscillations in phase and time. Q is the momentum of the spin wave, and omega q is the dispersion relation of the spin wave. So now when you have a many-body system, you can connect the microscopic Hamiltonian to the frequency of the spin wave. So the theory, which is old theory, but the application of it to dipolar system is actually reasonably recent. And it's something that dates from 2012 for the very first application in dipolar cases, and Tommaso actually developed a spin wave in a cleaner way. But essentially, making a long story short, you can start from this spin Hamiltonian, xx plus yy, do some kind of transformation where the sigma plus operator becomes the creation of a particle, the sigma minus the destruction of a particle, and you end up with what is called a Bogoliubov Hamiltonian, where you've got an interaction energy of the ground state above which you have some excitation, and those excitations are the spin wave. So that's the quantum description of the spin wave. The thing which is interesting is the fact that the frequency of the spin wave, so which is to say their energy, is actually related to the Fourier transform of the interaction between the spins. So this is a result which is really generic, but the application to dipolar systems have some kind of mathematical subtleties that you need to handle. But at the end of the day, this is what you have. And considering, so essentially you've got the 1 over r cube in our case, the Fourier transform, and depending whether you have ferromagnetic or antiferromagnetic order, you may have a plus or minus. So it means that the dispersion relation, which is related to this quantity here through this formula, can be different depending whether you have nearest neighbor interaction or long-range interaction. And this is illustrated here, where if you have ferromagnetic or antiferromagnetic order and nearest neighbor interaction, you would expect a linear dispersion relation as a function of the quasi-momentum. So essentially, you would have omega proportional to the modulus of the momentum of the spin wave in both cases. When you are dipolar, this is no longer the case. Essentially, you would find this kind of weird behavior in the ferromagnetic case, where the dispersion relation becomes square root of the momentum, while it stays for the antiferromagnetic linear dispersion. So this is a consequence of having 1 over r cubed. So this is the importance of being dipolar of the title. And if you want to understand why this is the antiferro, which is actually not modified, you can think of the influence of the frustration. The frustration is the thing which is going to make the interaction effectively short range, because it has a tendency to destabilize the antiferromagnetic order. So essentially, if you have an antiferromagnetic order, you will see that this has a tendency, this second order thing, to destabilize the magnetic order. So making the interaction effectively short range. So at the end of the day, it's not surprising that in the case of the antiferro, you do not find any difference between nearest neighbor and dipolar, but it does have a strong influence on the dipolar. So how do you measure that? I mean, the usual way of measuring the properties of the ground state properties on low-lying excitation of a system is to prepare the ground state and then create an excitation by neutron scattering, for example, in solid, and measure the dynamics. What Tommaso proposed is a different method, which is more suited to the systems we have, where you place the system you prepare the system out of equilibrium, and you try to measure the evolution of this out of equilibrium state. But the thing which is important is the fact that what you do after the quench, and is going to be illustrated on the next few graphs, is you place the system suddenly in a mean field approximation of the ground state. And the mean field is important here because it means it's nearly the true ground state, but with a little bit of extra stuff. And what are the extra stuff? Precisely the spin waves, because this is not the true ground state. So the true ground state is the mean field ground state plus some spin waves on top of it. So essentially what you prepare is the mean field ground state plus spin waves. The system can evolve as a function of time, and you can extract from this the part that oscillates in time, which is this. It turns out that the reason why it's very well suited to our platforms is because the mean field ground state of the systems in the XY Hamiltonian are easy to prepare. Why are they easy? Because actually, if you have a ferromagnet in the XY plane, this is the mean field approximation of the ground state of the system. If you have an antiferromagnet, this is the mean field approximation of the antiferromagnet XY, and those are easy to prepare. So as I said, when you've done that, the system evolves as a function of time, and you can access some interesting observables, which are the time structure factor, which is essentially the Fourier transform in space of the correlation of the ZZ spin. So essentially you measure the ZZ correlation as a function of time, how they evolve, Fourier transform the thing, and it's directly, with a bit of math, which actually Tommaso did, relate to should oscillate at twice the oscillation frequency of the spin waves at a given Q. So that's the underlying method. So place the system out of equilibrium in a mean field ground state. The little bit residual of excitation is the spin wave, and in this way you probe the low-lying part of the spectrum. So let's go there. So we prepare initially all our atoms in spin up. So spin up in our case means the P state. Okay, and so that's what it means. So you have prepared all the atoms in the P state. You apply a pi/2 pulse on the system that creates, you flips the spin in the XY plane. And from there, on this 10 by 10 array, we can measure the correlation function. So at the end, after a given time, we measure the spin of each atoms, create and calculate the correlation function, the sigma z term, which is to say the probability that if you have a spin plus at a given location, you've got another spin plus another location around. And you have this kind of 2D pattern, a Scholar state, which tells you that if it's positively, it's red, it's positive correlation. If it's blue, it's negative correlation. And as a function of time, what you see is the appearance, of some kind of time behavior in the correlation function. You can make this 2D graph a 1D graph just by simply integrating at a given distance. And in this way, you plot a spatio-temporal map of the evolution of the correlation as a function of time and distance. And the thing which you can read here, so this is the time, this is the distance, is that at short distance, nearest neighbor distance, you see the rapid appearance of antiferromagnetic correlations. You have these plumes of, positive correlation, and you can then apply the rule I was mentioning. So, I mean, the exact way of the behavior, the behavior is actually subtle to understand. This is non-trivial behavior, but if you do the Fourier transform in space at each time, you can plot this kind of evolution of the time-dependent structure factor, which does oscillate as a function of time. It's supposed to oscillate at a given frequency. Obviously, it does not, and the reason why it does not is because it's a finite size system. So there is a lot of complexity in analyzing those data that comes from the finite size systems of the finite size of the system. Essentially, the spin waves bounce on the surface and are reflected. So it means that the frequency is not a pure standing wave that you have in the system. Anyway, Tommaso and his colleagues spent a lot of time trying to analyze those data, and from there you can extract the dispersion relation as a function of the quasi-momentum. And you do observe something which, so the circles are the experiment, the square are actually the theory if you include the exact number of atoms we have in the system. And if you had a much larger system size, an infinite system size, you would have the square root. And even with actually 1,000 atoms, that wouldn't be exactly the square root because it's only finite size. So anyway, you do see that this is something non-linear as a function of Q. And if you repeat the exact same experiment for now, the antiferromagnet. So how do you do the antiferromagnet? Here there is a subtlety. The sign of the interaction is what it is. And in our case, this is a ferromagnetic interaction. But the thing which is subtle is that if now you start from an antiferromagnet along Z, you can prepare a staggered configuration of spin up, spin down. You place them in the XY plane by again applying a value pi over 2. You use the following trick. The highest excited state of the XY model is the ground state of minus the XY model, which is exactly what you have for the minus J. And the dynamics under minus H or plus H is exactly the same. So that's a very nice trick because it allows you on the very same platform to have a comparative measurement, ferromagnetic, antiferromagnetic, simply by changing the initial state you prepare. So we did exactly the same trick as illustrated here. And what we have now is something which varies linearly as a function of time. And so indeed, this is the signature that the 1/r cube does modify the dispersion relation. That was the first time it was measured on actually any platform. Okay, how much time do I have, please, Tobias? 2, 3 minutes, 4 minutes?
Technically 0, but please go ahead.
Okay, so the only thing I want to show you is how we can also, instead of looking at the low-lying excitation, to prepare the ground state of the system. And we do that in a 1D system, trying to map onto what is called a Tomonaga-Luttinger liquid. So the idea is that you take a chain, a 1D chain of XY model, and it turns out that if you use a continuous approximation of this system, you can map this XY chain onto something which is called a Luttinger liquid. So essentially now you will replace the sigma plus operator by some kind of field, a phase field, and the sigma z by some kind of gradient of a phase, and you have the integral of a harmonic oscillator. And that's a system that has been studied very extensively. And the hallmark of this system is that you should have power law decay correlations. And so now the whole system is defined by two universal parameters, U and K. And the K you can directly extract from the power law decay of the system. It turns out that there are other defining properties of the system through the response to impurities and how the correlation spread over the system, but essentially I will just use this. So now the question we're asking with Tommaso is that the canonical Tomonaga-Luttinger liquid is for nearest neighbor interaction. So is it again stable if you have dipolar interaction? Some prediction seems to say yes, with some kind of modify K and U. But also how sensitive is it to imperfections? So that's a bit the question we're asking with Tommaso. So I'm not going to go too much into the details, but essentially I will just show you how we can prepare the ground state of the system. And here the idea is to do an adiabatic preparation. So essentially you want to prepare the ground state of this Hamiltonian, but this is hard. So what you do instead, you start from an Hamiltonian which is easy to prepare. So you just apply an Hamiltonian which corresponds to all the spins pointing up and down by a staggered magnetic field. So this is the field that dominates. You prepare the ground state of this Hamiltonian, and you will lower delta in order to branch onto the ground state of this XY Hamiltonian. So this can be done with laser beams that mimics a magnetic field. And so essentially what we do is we adiabatically drive the system from the ground state of the HD Hamiltonian onto the ground state of the XY. And depending on where we start in terms of delta configuration, we can either branch onto the ferromagnetic case or the antiferromagnetic case, again, independent of the sign of the interaction. So that's kind of a nice trick we can play with those artificial systems. So we've done that in a ring, about 24 atoms, initial preparation of the staggered configuration, and then we adiabatically drive down the amplitude of the lasers in order to connect to see the magnetic, so we measure as a function of time, sorry, the magnetization. And what we observe is that starting from a magnetization in the, you have two sets of atoms, the one with a spin up, the other one with spin down. And as you, along Z, but as you do the adiabatic preparation in the XY plane, the magnetization should actually melt to 0. And this is what we observe here. And together with the appearance of ferromagnetic correlation if we are in the ferromagnetic case, and antiferromagnetic correlation if we are in the antiferromagnetic case. The thing which is interesting was that those correlations as a function of space, which are represented here, I can measure them as a function of distance in order to try to extract the K coefficient of the Luttinger liquid. And that's what we've done for the ferromagnet and the antiferromagnet. And the interesting thing is that it was kind of the first time people had seen some kind of power law decaying correlations as a function of distance in the system. Okay, so it's a bit technical all this, but essentially the bottom line is that you can access low energy physics of this thermonaga liquid and directly observe the correlation that was very hard to observe in any other system. So that's what we did with Tommaso. We did compare with models including imperfections and how close we were to instability point of the Luttinger liquid. Okay, so that's all I wanted to say. But so essentially, the other thing that we've been looking at is in the out of equilibrium setting, the appearance of these spin squeezing. I mean, it turns out that at short time, you do observe that the fluctuations of the spins are actually decreased with respect to independent spins. And we've essentially enlarged more recently to the physics of spin one, or if you want, trying to look at the propagation of holes into a ferromagnetic background. So I'm not going to discuss that too much, and I stop here, and sorry for having been long.
Thanks a lot, Antoine. Oh, that was very nice. I think it was very, very good to follow. So let's use some time for questions now. If you want to ask anything, understand something better, have further ideas, just unmute yourself or react with hands up and ask whatever comes to mind. Maybe I actually start myself because I'm not an expert on Rydberg systems, but I just wanted to ask the system that you have in the beginning, you map basically to spin 1/2, right? But can you also address multiple internal levels and then have, let's say, spin 1 or spin?
Yeah, so that's a good question. So, I mean, the work I was describing here goes in this direction.
Right.
So we use 3 Rydberg states, NP, NS, N plus 1S. So let's say 60S, 60P, 61P. They are nearly equidistant. So this object is a bit equivalent to a spin 1 system. That's not exactly the way we're looking at that this way for this experiment. We're rather trying to encode the physics of doped magnets. So we're just saying that the P state is like a hole, and the N plus 1 and S states are spin up and spin down. And you look at the propagation of the holes. So of course, no particles propagate. We're just talking about exchanging the states of the atoms. But that goes exactly along the direction you're asking. So.
Okay, that's nice. And maybe another more technical question, actually. So you're often interested in measuring two-point correlators, right? And I was just wondering, what are the typical sample sizes you have in these experiments? So how much statistics do you have?
Okay, so that's a good question, actually. For each of the points that we show on the experiment, so let me just take whatever, like for example, this one. So we try to measure the ferromagnet correlation at this particular moment. So essentially we need, of course, the way we measure the Rydberg is a destructive measurement. So far, everyone does it this way. There are very only recently people managed to do some non-destructive measurement. Most of the people still do the destructive measurement. So you destroy your sample, you need to rebuild it, and typically you average between 100 and 1,000 times, depending on the error bars you want to have. Okay, so it means that acquiring this, and the machine operates at, let's say, a few hertz. So you see that to acquire the whole curve takes 1 or 2 hours. And this time is independent of the size of the system, right? So this is 24 atoms. For the first experiment I was describing that we did with Tommaso, the quench spectroscopy, we were using 100 atoms. And 100 is also, it's an interesting regime because this is a regime where actually it's very challenging to do calculation. Tommaso will mention that a bit more. Of course, there are regimes where we know how to do calculation, but in the case of antiferromagnet with frustration, this is challenging. So yeah, and so typically, again, for each of these correlations, this corresponds to, this is a single shot, and we average over many of these single shots.
Okay, so typically between 10 to the 2 and 10 to the 3.
Yes.
Okay,
yes.
okay. Yeah, I think this is kind of...
Yeah, I mean, the error bar, if you wish, roughly speaking, it will set your error bars. I mean, if you say that you are dominated by, how do you call it, standard quantum limit, this is the square root of the number of shots. So if you want 3% of noise, assuming that everything else is perfect, it's 1,000 measurement.
Exactly. Okay, thanks.
And are those long-range correlations harder to measure? Is it?
Sorry, I missed the beginning of your the question.
Is that long-range correlations harder to measure? Is it some technical difficulty to measuring long-range correlations?
No, I mean, for us, the thing which is hard at this level is for the theorists. Because for us, in a sense, it's the very same experiment, whether you got long range or short range. It's just that the physics is richer and more interesting when it's long range. But I mean, the experiment is exactly the same.
Okay, thanks.
Further questions for Antoine? Okay, you also have the chance later, so don't worry. Let's thank Antoine again. Thanks a lot. And let's welcome Tommaso for the second half.
All right, let's see. Yeah. Okay. Okay, I think you can see my slides, I presume, and my pointer. So let me start by thanking Toby and his fellow co-organizers so very much for the very kind invitation of putting together this series of seminars. It's very interesting. Also, for bringing together two different sides of the same story, which is rather original, I think, and stimulating. So I actually take the boring side of the story, which is the theoretical one. Somehow, you got the real thing, and now you get the hypothetical thing, maybe. Okay. So, but I'll try to be as entertaining as possible. We'll see how far I get. But let me start by actually thanking some of the real players of this work. Antoine already nicely mentioned them: Saverio, Fabio, and Filippo here in Lyon. But of course, nothing. I mean, I think I won't be here if it were not for the collaboration with Antoine and also with Norman Yao's group at Harvard. So I'll structure my part of the presentation in two parts. So one about how we go about and simulate Antoine's machine somehow, and beyond simulating, actually, how we try and understand the physics that goes on there. And a second shorter part about extending the concept of quench spectroscopy that Antoine has already developed to more exotic excitations beyond spin waves that you've heard so far. Okay, so first part about classical simulation and understanding of simulators, and I'd like to really distinguish somehow the two concepts of simulating and understanding. They're not necessarily equivalent. So this cartoon here suggests how we sit as theoreticians. So we sit on the classical side of the world trying to observe the quantum one, but you're kind of slow, like a snail. Okay, so we'll be soon outpaced by the quantum realm, I guess. Anyway, so in general, what we do in Lyon is to study the dynamics and also equilibrium properties of a class of models within which Antoine's experiment fits so nicely, which are models of spin systems with power law interactions with U1 symmetry. Their dynamics is beautiful, generates lots of very nice entangled states, as Antoine has already mentioned. So this is like the broad picture of the setups that would realize such a model. So it's really a widely realizable with state-of-the-art platforms in quantum simulation. The hero of today, of course, is the dipolar interactions, but some of the things that I'll say later also apply to shorter range interactions, to this alpha exponent not being necessarily 3, but even larger. Okay, but you can also have atoms in cavities and have all-to-all interactions these days. Anyway. So now back to the specific topic of resonantly interacting Rydberg atom arrays. So how hard is it to simulate them as a theoretician? So first of all, I should say that the fermentalists are pretty kind to us because they do not realize generic evolutions. Also by definition, somehow the generic evolutions are not so interesting at the end of the day. So you have to be, to search for some special physics. And non-generic means actually easier to simulate. So in particular, all the experiments that Antoine has described, they are carried out at relatively low energies, either explicitly targeting the ground state or realizing low energy quenches. So when it comes to the one-dimensional world, that Antoine described at the end of his talk. So there we encounter not so wild problems like this cat here. So the one-dimensional dipolar systems, they can be understood rather well. Antoine has already described latent gel liquid theory as a theoretical framework. And at the numerical level, instead, because you are working at low energies, you have in general low entanglement developed in the evolutions. And so matrix product states are pretty much all it takes to quantitatively describe the experiments. As long as you are working in the unitary regime, then it becomes more difficult at the end of the day to take the unwanted effects even for the experimentalists into account. So to take into account imperfections and so on to actually try and match with Antoine's results and his colleagues' results. On the other hand, wilder things live in the two-dimensional world. So two-dimensional systems are harder to tame. But among these wilder animals living in 2D, there are some that are not too wild, and as such is the dipolar ferromagnet. So the dipolar ferromagnet, first of all, lends itself very nicely to calculations in terms of equilibrium properties. It's a ferromagnetic model. It's something that people maybe would have considered rather boring in the world of quantum magnetism, were it not for the beautiful realization of its dynamics. But for the equilibrium level, it is it's an innocent ferromagnet that can be treated with quantum Monte Carlo, and also can be understood somehow semi-analytically by invoking the fact that it has a long-range ordered state and spin wave excitations. And Antoine has already developed this concept quite a bit. Now, when it comes to non-equilibrium physics, well, things get more interesting, but luckily they still stay rather treatable. So in particular, our workhorse to have the ultimate quantitative understanding is using time-dependent variational Monte Carlo. That is, we guess the wave function of the system somehow, and we evolve it with the so-called time-dependent variational principle. And the wave function we use is somehow the simplest one you can imagine, that retains some entanglement, beyond the mean field approximation. It wouldn't have any entanglement, and it's what people can call a pair product state or a spin Jastrow state that has, in which the coefficients by construction are factorized into objects that correlate pairs of spins. Okay, so these actually works rather well for the systems that I'll show you in a moment. Another approach which is rather effective for dipolar interactions and has been used in the recent past is a semi-classical approach, the discrete truncated Wigner approximation, which essentially mimics the quantum dynamics by generating a sample of trajectories for a classical system and averaging over them. And it's impressively effective in some situations as well. All right, so just as a proof of how these methods work, so this is the graph you already seen from Antoine's talk, showing the correlations among the z-spin components that spread over time after a quench from this coherent spin state. And these are the theory graphs for the same thing. So you see the TVMC and the truncated Wigner approximation. So they both do a pretty good job in picturing, in reproducing, even the finest features of the experiment. In particular, TVMC is impressively close. Okay. In particular, you see this fundamental feature that correlations spread rather fast. In fact, they spread somehow with a sort of parabolic shape, so they spread faster than linear, at least at short distance. Okay, then as to understanding these dynamics, well, there it takes some approximations that appeared at the beginning rather arbitrary, but they're rather controlled in the end. So the theory that Antoine mentioned, which is somehow a generalization of spin wave theory to also take into account nonlinear degrees of freedom, is what we like to call rotor plus spin wave separation, which allows to rewrite the Hamiltonian of the system that I wrote before with two terms. One that describes the collective spin dynamics, essentially the zero momentum degrees of freedom of the system, but projected onto the subspace of Hilbert space in which the collective spin has maximal spin length, the so-called decay states. Okay, and the Hamiltonian, when projected onto this manifold, as the form of a so-called planar rotor Hamiltonian, or also known as one-axis twisting Hamiltonian for the experts. And then there are the finite momentum degrees of freedom that within the first approximation can be represented as linear spin waves. Okay, and in principle there are other terms that couple these two degrees of freedom, but if the spin waves are mildly populated in the dynamics, then these further terms can be safely neglected. And you know, and then one sees, sorry, I should have stressed this aspect, one sees essentially in the dynamics kind of two decoupled degrees of freedom that are individually in some sense integrable, especially the spin wave part is just a collection of harmonic oscillators. So this is a rather simple dynamics, but also unsettlingly simple, given that we are working with in principle with a two-dimensional nonlinear system that should not be so simply understandable. So to prove that this separation works, we did some earlier work before the work that we did for Antoine. So for instance, looking at how the rotor dynamics manifests itself. You see it rather strikingly if you look, for instance, at the fluctuations of the collective spin component, which is initially polarized at the Jx1, and you observe these huge peaks that correspond in fact to the formation of Schrödinger's cat states, or close to Schrödinger's cat states. They are a typical feature of one-axis twisting dynamics, as known from the all-to-all interacting system. And then instead, if you look at the correlations, you see spin wave dynamics. Already Antoine has shown this plot of the time-dependent structure factor, where we compare here the experimental data with linear spin wave theory, which are the dashed lines that do a pretty decent job, and in particular reproduce some sort of persistent oscillations at long times. So you have, in both cases, persistent dynamics, which shows that there there isn't an equilibration between these various degrees of freedom. Okay, so no obvious thermalization. On the other hand, there are wilder things out there in the world of two-dimensional systems, and that's the dipolar antiferromagnet. As Antoine has already mentioned, that has the specificity of being frustrated. And first of all, frustration, when it comes to numerics, has a very strongly hindering effect that we cannot do the thermodynamics anymore so efficiently. We have a sign problem in quantum Monte Carlo, and even looking at the ground state is a bit of a challenge. And when it comes to the dynamics, well, there is actually a very interesting aspect to me, which comes along with frustration. The fact that, first of all, the mean field ground state that we prepare the system into, that the experiment prepares the system into to initialize the dynamics, is actually of higher energy compared to the ground state than it is in the antiferromagnet than it is in the ferromagnet. So you have a quench at high energy, which should develop, somehow thermalize to a state that is of higher effective temperature. It has less correlations, but at the same time, it must have more entanglement entropy. So you have, in fact, more hidden correlations between every two a subsystem and its complement. So you have correlations that are less easy to read. So as a matter of fact, if you look at the correlation spreading in antiferromagnet, the same correlations as shown before, but now with frustration, you see that they seem to spread only for a short time, and then they die out somehow. And this feature actually, so the absence of long-range spreading correlations is a difficult thing to reproduce, because if you go about and do TVMC for this problem, it turns out that TVMC wants the correlations to spread over long distances instead. And it's only within the targeted linear approximation that we observe, in fact, a better match with experiment and correlations that don't spread until all over the system. So, so this behavior here seems to suggest that there is some sort of fast thermalization to a situation with short-range correlations. You could somehow say that maybe here you have reached a state which is already equilibrated, but at least as far as two-point correlations are concerned. Okay, so along with this short-ranged nature of correlations, there is also an accompanying different nature of the excitations in the system, which are don't seem to be any longer free bosonic quasi-particles, as they appear to be in the case of the ferromagnet. And this is again strikingly observed when looking at the time-dependent structure factor, where you see that if the spin wave prediction shows very persistent oscillations, the experimental data in fact show damping at essentially all wave vectors that we can look at. Okay, and this is not a feature of a defect of an imperfection of an experiment that may exhibit dephasing or whatnot, because you see it also in the case of systems, system sizes, where we can simulate pretty much everything there is, including imperfections, and we see the same effect of damping with or without imperfections. Okay, so it's a truly true feature of the unitary dynamics of the system. Okay, so where does this damping of oscillations and instability of spin wave excitations come from? There are two options that are on the table, and I don't think we can resolve for one or the other at the moment, or or for both. So one is the fact that the specific dispersion relation of excitations in an antiferromagnet, as Antoine has shown, as some sort of linear behavior, in particular a persistent linear behavior in the two-dimensional dispersion relation if you move along the diagonal in the Brillouin zone. And if you have a linear dispersion relation, you can have one magnon, one spin wave, decaying into three by the nonlinearities of the Hamiltonian, conserving both momentum and energy. So you have resonant decay processes that may lead to finite lifetime for spin waves, at least at the boundaries of the Brillouin zone. But in the experiment, we're not working with individual injected excitations, nor are we in the calculations, although we could. But actually, the quench injects a finite density of such excitations. So there are interactions effects among them that may also be responsible for their decay. Okay, so I think that we still cannot resolve whether it's one effect or the other or both. They are fundamental, and this brings me to the partial conclusion of my of this first part. Second part being shorter, just for to reassure the organizers. So the ferromagnetic interactions appear to lead to non-thermalizing dynamics. That can be efficiently described actually by its non-thermalizing behavior somehow and also understood. Whereas the antiferromagnetic interactions may actually be leading to rapidly thermalizing dynamics. I stay with a question mark because to know that you have thermalization, you should be able to compare with the thermal state, but we do not have reference data for the thermal state because we don't have quantum Monte Carlo, for instance, for this problem. Okay. And this rapidly thermalizing dynamics resembles a bit more what you would have in generic systems, I guess, and it's harder by this token to describe and understand. As a partial outlook, it definitely we would need to look more systematically what happens if we lower the energy of the initial state so as to have parametrically less of these excitations in the antiferromagnet and understand what is the origin of their instability. And also extend the same logic of looking at the dynamics of the correlations to extract the information on excitations to frustrated systems other than the frustrated square lattice that the experiment has realized. Okay, so this brings me to my last part, where I'd like to go beyond the by now conventional picture of quench spectroscopy and go to unconventional territory, trying to extract the nature of excitations that are in fact of fermionic try to extract the existence of excitations that are of fermionic origin or nature. All right, so in particular, so far you've seen the mapping of spins onto bosons, as Antoine has mentioned it, but there's another famous mapping of spins onto particles, which is the Jordan-Wigner transformation. And that's actually a high no local transformation. These Jordan-Wigner fermions are essentially like comets. They have a spin operator followed by a tail of spins, so as to of spin operators, so as to satisfy the correct anti-commutation relations. Okay. Now, if you take in particular a one-dimensional system, that's where this approach is most appropriate. One-dimensional chain with power law interactions. Let's say in this case I'll limit myself to the XY interactions. Yeah, and to make this transformation, then you recover a model of interacting fermions, interacting because this model describes hopping of fermions between two sites, neighboring or far apart, conditioned on the occupation of the in-between sites. Okay, but if you take short-range interactions, that is, nearest neighbor interactions, I should say, so alpha equals to infinity here, then there's no in-between sites, and so you have actually a free fermion model, which is extremely fascinating because somehow you reveal the integrable nature of this model. That's a very well-known thing. So this is a very old result. It is probably 60 years old. It dates back to Lieb-Mattes and Schulz from the beginning of the 60s. But can one see actually these fermionic excitations in an experiment? So that's kind of the challenge. And I would claim that there is no clear, no direct observation of these excitations to date, but that quantum machines can do it. Okay, with quench spectroscopy. So let's see how. So I'll now specialize to this one-dimensional XX nearest neighbor chain, which is completely mappable onto free fermions, and again repeat the same logic of the experiment that Antoine has performed, but now it's a thought experiment, it's a theoretical experiment. So we start from the coherent spin state, which in the fermionic language is, it's a pretty funny state. Is actually the superposition of all possible Fock states, equally weighted. All right, and it has a momentum distribution which is nothing like a Fermi C. Okay, so not a step, but really a rounded thing. Still, it's half field on average. You have many fieldings, but on average, it's half field. Okay, so and then if you look at what the spin operators do to this state, in particular the Fourier transform or the SZ operators, well, it's something that would introduce excitations on this initial state by generating particle Hall pairs. So it's by promoting particle at momentum k to particle at momentum k plus q, where q is the index of this operator. And this, this operator can act pretty much all over the states that are accessible to these fermions, because they're all occupied in this initial state, as shown by this distribution. Okay, so now if you are doing quench spectroscopy based on spin-spin correlations, what you're going to probe at the end of the day is a spectral function, which will be a further Fourier transform compared to what we have discussed so far. So you do the spatial Fourier transform or the spin-spin correlations to get to this Q minus Q correlation, and then a time Fourier transform to get to a full spectral function, what's called the quench spectral function in this business, and which what it does, it probes transitions between excited state, between eigenstates of the Hamiltonian that are connected by the application twice of this SQZ, S minus QZ operator, that is the creation of two particle Hall excitations. And particle Hall excitations, as you can see from this picture, at the same momentum Q can have many energies. You can excite particles down here or particles up here. You get different excitation energies, but same momentum. And so you have, as a result, a continuum of excitations. So you have this characteristic particle Hall continuum, which appears in this quench spectral function. It is a structured continuum because you have a different density of states when you are at the bottom or at the center of the, or at the at the halfway between the center and the edge on the Brillouin zone. But still it's a continuum. Okay, so you don't see the actual free quasi-particles. To see the actual free quasi-particles, what you can do instead is to do some non-local quench spectroscopy. That is to try and target the fermionic correlation functions, not the spin-spin ones. So the beautiful thing about the Jordan-Wigner transformation is that it gives you a way to translate fermionic correlations into spin correlations. In particular, the most interesting ones are pairing, like anomalous correlations, Fi, Fj, plus its complex conjugate, that translate in the spin language into correlations between two sides, between the x and y components, with a string of Z operators in between. And this looks like a complicated object, but in fact, experimentalists have become able to measure, so in particular, Antoine and his collaborators have become able to measure these objects in the recent past. They can use different measurement bases for different sides. So this is definitely accessible to experiments as far as I understand. Then Antoine maybe can rectify that. Okay, so with this idea in mind, then one can look at how the double Fourier transform in space and time of this fermionic correlation function would behave. Well, I guess maybe at some point you may already know what's going on here. So this quench spectral function, it is probing the transitions between eigenstates that are induced by creating or destroying two particles. Okay, so what it's going to probe is the cost of two particles or two holes at opposite wave vectors. And maybe unsurprisingly, what you get is a nice cosine band, and it's inverted, an inverted version of it, which corresponds to the energy to create two particles or two holes. Okay, and that's and this structure here becomes very sharp, with system size. With the bigger the system size, the sharper it gets. Okay, and this is all done with periodic boundary conditions, but as you've seen in Antoine's experiment, also periodic boundary conditions are not, a theoretical construction. They're completely accessible to the experiment. Okay, so to finish, let's go now to the more relevant case of dipolar ferromagnetic exchange. So now you have interacting fermions because this conditional, the hopping between sites becomes conditional on the occupation of the in-between sites. And now, if you do, again, the local quench spectroscopy, or the one based on spin-spin correlations, you again observe a continuum of excitations. So that's nice. You would see this fundamental feature also in dipolar chains. Now, what happens if you look instead at the non-local quench spectroscopy? So before I flash the slide, the figure, let me just say that it's well known that interactions for one-dimensional fermions should change the physics radically compared to non-interacting fermions. So they should discard, in fact, the Fermi, the free fermion picture. There's no Landau Fermi liquid in 1D. So in principle, one should expect to have ill-defined quasi-particles. But if you look at in practice, the results, you still observe a cosine band, as if you had, well-defined quasi-particles. So then the whole business is to observe, and that's what we're doing at the moment, is to observe how sharply defined this cosine band really is. So how the width in energy of this feature scales with system size. And it still appears to be rather sharp in the case of some interacting fermion systems, but this is still a work in progress. So to conclude on this part, definitely we think that we can for the first time reveal the intrinsically fermionic nature of excitations of spin chains using no local quench spectroscopy. And I would like to stress that this is something which, in my understanding, is fundamentally inaccessible to local probes, such as neutron scattering, that probes only 2-point correlations, but not correlations with more degrees of freedom. So that would really be a very positive contribution of quantum simulators beyond what everything that can be done in condensed matter to even understand things that in principle are under the watch of condensed matter physics and have been for a long time. One thing that can be observed in these experiments is this subtle breakdown of the Landau Fermi liquid paradigm that's on the outlook part. And also one can think bigger now and think of using the flexibility in the geometry that Antoine has exhibited to take not just one chain, but maybe 2 chains or 3 or more, and couple them progressively as per the dipolar interaction that just depends on the distance. And go from 1D to quasi 1D and probe to what extent fermionic quasi-particles actually can exist in 2 dimensions as well, in quasi 1D systems rather, or introduce more frustration in the system than the one we've seen so far, and go to regimes in which the excitations are no longer spin waves or unstable spin waves, but they are fractionalized objects that probably can only be detected positively by using no local correlations like the ones that we are proposing. And with this, I thank you very much for your patience and attention.
Thanks a lot, Tommaso. All right. So again, we have time for questions. Let me maybe just start, because something in the middle, I was confused by something. You showed this graph where you essentially had, I think it was the variance, or technically the Fisher information.
Yes.
I think it was still in the ferromagnets.
Yes. Where do I have it? I'm sorry. I guess you're talking about this one, maybe.
Yes, exactly. So what is the intuition behind getting at some time scale these super strong peaks?
Well, I think it's kind of it's certainly beyond my intuition. So, but if you take the all-to-all interacting version of the models that we look at, so the alpha equal to 0 limit, this one-axis twisting Hamiltonian. So somehow, you can think about it this way. So the Hamiltonian conserves the collective spin, and if you start from a state that has collective spin of maximal length, the whole dynamics takes place in a space which is only n+1 states for n spins. Okay, n spin 1/2. And so you have a very reduced space in which the dynamics is taking place. So in small Hilbert spaces, there are wild things that can happen. So typically you have recurrences, which is not what's observed here. So this is recurrences, you get them later, and you have perfect periodicity of the dynamics over time scales of order n, which is completely legitimate if you have a small Hilbert space. So the appearance of a Schrödinger's cat state, like this one here, well, this is something that it's rather, yeah. So analytically easy to understand if you work out the math of that problem, because at the end of the day, it's kind of a simple problem, living in a small Hilbert space. It comes from a special accumulation, a special, evolution of the different phases of the components of the wave function that conjure to build up a superposition between all spins along x and all spins along minus x. Okay, so if you have a quantum optics taste, which I think you do, you have the same phenomenon. If you look at a Kerr nonlinear single mode, where you also have squeezing at short time, which is the analog of spin squeezing, as Antoine has mentioned. But then at later times, you have, in fact, the formation of cat states in the bosonic realm that they are the counterpart of the Schrödinger's cat state. So, so if that builds some intuition for you, then then maybe I've done my job. Otherwise, one has to do the math, as far as I'm concerned.
No, definitely helps. Thanks. But I think shut up and calculate is sometimes also good advice. I have another question, which concerns this idea of mapping fermionic correlators to spin correlators. So this is, of course, highly non-local. And I was just wondering whether this is something you can do to obtain the full counting statistics. Because I can imagine that the mapping is different for correlation functions of different orders. Is that true?
Okay, so you're thinking of the full counting statistics for the fermions.
Yes, exactly.
Okay, that's a very interesting question, and all right. So it depends what you're looking at. So I'll start say on the easy side, and then maybe I'll disappoint you later. But so if you look, so something I have not written here, but if you just look at the fermionic density, so that one thing is, so the number of fermions at each side, that is local in the spin. So it's the same as, well, actually, you can see it here. So this is like the number of fermions at side L, okay? So in that case, we have the same full counting statistics. If you look at anything, in the Z basis, it's the same full counting statistics for fermions or for spins. If you look off diagonal, yes. So I guess that gets rather challenging. So I think so. Looking at or no, so I don't know. One has to do the math again, which we have not done, to be honest. So if I, for instance, ask myself what happens to a 3-point correlation function, so I'm, instead of looking straight at the full counting statistics, I moment by moment, let's say. Okay.
Yes.
Then I would say that it's still something, which is I guess, okay, maybe I'll be more positive. So it may not be much more challenging in terms of excuse me, I had it where did I have it here? Yeah, it may not be much more challenging than reconstructing this kind of objects, because if you think about it, if you have 3 sides, what you're going to get more at worst is like that you have 3 spin operators and string operators connecting the various sides. So yeah, so you already are hitting like the worst case scenario in terms of the amount of degrees of freedom or the amount of spins that you have to measure, let's say in an experiment, for instance, simultaneously when you look at 2-point correlations. So my understanding is that it's not too bad. So we identified, in fact, from the practical point of view, an element which may degrade the quality of the results for this no local quench spectroscopy compared to the more conventional one, which is the fact that intrinsically you have to measure a parity here. So okay, that's like the parity of the spin configuration on the string, and parities are extremely sensitive to any error that you can have in the readout. Okay, so you mess with it. So But essentially, what an error would make for you is that it would make what appears like a long-range correlation, for instance, it makes it somehow effectively short range. So it introduces a decay length, which is completely artificial. It just comes from the readout, and it's the exponential of with the length, sorry, with which diverges if you send the error rate to zero. Or it becomes or it becomes somehow zero if you send the error rate to maximum, so like to getting essentially random results. So at the end of the day, what consequence does this have? I'm actually not answering your question anymore. I'm sorry, but I'm taking the opportunity to elaborate. So this would have the consequence. And then also in full count statistics, this may be the case. So at least here, practically, what we observe is that you get correlations that are less well defined in real space. So that means that become broader in momentum space. So we get a broadening of these features in momentum. So, but the overall features are fine, even with important error rates. Now, if I have to imagine what the effect is on the estimation of higher moments, I guess this is going to be also problematic, but one has to go in practice and see.
Yes. Yeah, it was basically motivated by understanding, okay, the second moments, of course, give you information about the spectrum, essentially, which is what you have done over and over now. Yes. And I was just wondering whether trying to probe higher order correlators tells you something about the processes that are going on there, like the interactions between quasi-particles and something like that.
Yes. That is certainly with that's very interesting. We didn't think about this. Then you would very, very interesting. We should look into that. For instance, one could see whether we can kind of estimate the rate at which particles interact, for instance, or something like that. So
yes.
Excellent suggestion. We should. I take it, and come back to you if I have results in the future.
Thank you, Tommaso. Do we have further questions for the audience? I'm sorry that I'm taking so much time.
No, it's me who was long.
So I take this as a no for now. And therefore, I thank our two speakers again. These were excellent presentations, in particular for qmeets. I think it was very understandable. And we wish you nice evening, nice Christmas time. And for those of you who are interested, come back in January, where we have one of the biggest people currently in quantum thermodynamics, which is Nicole Younger-Halpern. All right. Goodbye, everyone.
Thank you.
Thank you, Toby, very much. Yeah.
Bye.
Bye-bye.